guys, in this video I am talking about chapter number 14, electromagnetism part 2. Magnetic flux and flux density. Like electric flux is the magnetic flux through a plane element of area in the uniform magnetic field. B is given by dot product of B and A. Note that A is a vector whose magnitude is the area of the element and whose direction is along the normal to the surface of the element. From theta is the angle between the direction of the vector B and A. The field is directed along the normal to the area of so theta is 0 and the flux is maximum equal to B A. When the field is parallel to the plane of the area, the angle between the field and normal to area is 90 degree. Theta 90, so the flux through the area in this position is 0. In case of curved surface placed in the non-uniform magnetic field, the curved path surface is divided into a number of small surface elements, each element being assumed plane, and the flux through the whole curved surface is calculated by the sum of contribution from all the elements of the surface. From the definition of Tesla, the unit of magnetic flux is nma-1, which is called Weber. According to the magnetic induction, B is the flux per unit area of a surface perpendicular to B. Hence, it is also known as flux density. Its unit is then WBm-2. Therefore, magnetic induction, the magnetic field strength is measured in terms of WBm-2. Ampere's law and determination of flux density B. We know that an electric current produces a magnetic field. Ampere, after carrying out a series of experiments, generalized his results into a law known as Ampere's circular law, by which the magnetic flux density B at any point due to a current carrying conductor can be easily computed as explained below. Consider a closed path in the form of a circle of radius enclosing the current carrying wire. This closed path is referred as Ampere path. Divide this path into a small referred as Ampere path. Divide this path into small element of the length like delta L. Let B be the value of flux density at the site of delta L. Determine the values of B dot delta L if theta is the angle between B and delta L, then B dot delta L equal to B delta L cos theta. B cos theta represents the component of B along the elements of length delta L, component of B parallel to delta L. Thus, B dot L delta L represents the product of the length of the element and the component of B parallel to delta L. Ampere started at that. The sum of the quantities B dot delta L for all the path elements into which the complete loop has been divided equals times the total current enclosed by the loop, where 5 micro is a constant known as permeability of the free space. Its SI unit, its value is 4 pi multiplied 10 to the power minus 7. This can be mathematically expressed as where is the value of the B dot delta L along the element, and n is the total number of elements into which the loop has been divided. This is known as Ampere's critical law. Field due to a current carrying solenoid. A solenoid is a long, tightly wound cylindrical coil of wire. When current passes through such a coil, it behaves like a bar magnet. The magnetic field produced by it is shown in the field inside a long solenoid. The field inside a long solenoid is uniform and much strong, whereas outside the solenoid it is so weak that it can be neglected as compared to the field inside. The value of magnetic field B can be easily determined by applying Ampere's critical law. Consider a rectangular loop A, B, C, D. Divide it into 4 elements of length AB equal to L1, BC equal to L2, CD equal to L3, and DA equal to L4. Now we will calculate the value of B dot delta L for each of the elements. First, we will consider the element AB equal to L1 that lies inside the solenoid. Field inside the solenoid is uniform and it is parallel to L1. For the element CD equal to L3 that lies outside the solenoid, the field B is 0. Again, B is perpendicular to L2 and L4 inside the solenoid and is 0 outside. So, to find the current enclosed, consider the rectangular surface bounded by the loop ABCDA. If n is the number of turns per unit length of the solenoid, the rectangular surface will interrupt and L1 turns, each carrying a current I. So the current enclosed by the loop and L1I, thus Ampere law gives the field B is along the axis of the solenoid and its direction is given by right hand grip rule, which state hold the solenoid in the right hand with fingers curling in the direction of the current. The thumb will point in the direction of the field. Okay guys, thanks for watching this video. Please subscribe my channel and like this video. Bye guys.